Chapter 2. Designing the Air Dispersion System. Welcome back to Chapter 2 of the AHC-Fabric Tutorial Series. In this session, we will look at how to model air dispersion features, such as orifices and nozzles on a fabric duct, using the design stage. The goal of this chapter is to understand how we can define perforation patterns on fabric duct pieces and prepare the system for airflow validation.
Once the fabric duct layout is ready, we can move into the design stage. The design stage interface is organized into multiple working areas: 2D panel at the top, orifice angle view, 3D viewer at the bottom, connection viewer on the left side, properties panel on the right side. All these windows are collapsible, and they can also be maximized depending on what you want to focus on. Before we proceed further, let us quickly go through a few important notes. First, air dispersion design is currently allowed only on straight duct pieces. It is not supported on reducers, elbow bends, or T-connectors. Second, the orifice calculation module generates the placement, size, and flow capacity based on simplified rules. If required, users can connect with us to customize the orifice calculation section as per their own internal calculation methods. Third, nozzle support is planned for the near future. To begin designing perforations, select the duct piece or component of interest. Once the piece is selected, you will see an option to Add Orifice Family. Click on this option to open the perforation design controls. This allows us to design perforations in a simple and structured way. Now, let us understand one of the most important concepts used in AHC-Fabric. Orifice family is a group of orifice rows that share the same design parameters, such as perforation size, pitch, initial offset, flow distribution pattern. This grouping makes it easier to create similar perforation patterns at different clock positions. For example, you may want to create one large orifice row at the 6 o'clock position and 4 smaller orifice rows at 4, 5, 7, and 8 o'clock positions. Instead of manually defining every row one by one, you can create a family for each unique design and then assign rows within that family. This helps reduce repetitive work and keeps the air dispersion design clean and manageable. For round and half-round ducts, when placing orifices, define the angle or clock position from the direction of airflow. Imagine standing in front of the duct opening with the airflow coming toward you. From this viewpoint, measure the orifice positions in the clockwise direction. For example, 0 degrees is at the top, 90 degrees is on the right, 180 degrees is at the bottom, and 270 degrees is on the left. In the 2D viewer, you can see an illustrative flat pattern of the fabric duct. Here, the orifice positions are clearly visible, along with their angular positions, pitch, and initial offset. Let us define two important terms here. Initial offset is the distance from the start of the fabric duct piece where there will be no orifices. Pitch is the distance between two consecutive orifices in a single row. These two parameters help control where the orifices start and how they are distributed along the duct length. Next, let us look at the orifice angle view. This view provides a sectional representation of how air may be projected into the space from different angular positions. It is important to understand that this is a ray projection view, not the actual CFD airthrow result. This view is mainly provided to help users get started and understand the maximum geometrical throw direction available from the selected orifice angles. Actual air distribution will be verified later using CFD analysis. Now, let us look at the Properties panel on the right side. This panel contains multiple sections. The first section is Flow and Pressure. Here, you can see the dispersion flow rate for the selected duct piece and the approximate static pressure available at that piece.
The next section is Design Parameters, which is specific to the selected orifice family. Here, you can define the orifice family flow rate. The sum of all family flow rates should be equal to the total flow rate of the selected duct piece. You can also define the end air velocity, which represents the expected air velocity near the occupied zone or at the reference height. The air throw value defines the expected throw distance from the orifice. You can configure the number of orifice rows in each family and assign an angular position to every row. You can also define the initial offset for the rows as required. The next section is Orifice Details. By default, AHC-Fabric automatically calculates perforation details such as orifice size, flow through each orifice, pitch, number of orifices. However, users also have the option to manually enter or adjust these values as needed. This gives flexibility to either use automated calculations or apply your own design preferences. AHC-Fabric also includes clear and robust validation checks to prevent incorrect designs. For example, the system checks for issues such as insufficient row spacing and overlapping orifices. These checks are important because such issues can create serious manufacturing and performance problems if they are not detected early. With these validations, the user can confidently design perforation layouts before moving to analysis and manufacturing. In this way, every straight duct piece can be easily modeled with its required air dispersion design. AHC-Fabric also provides a simple copy-paste workflow, allowing users to duplicate the same perforation design across multiple ducts with ease. This is especially useful when several duct pieces follow the same air distribution requirement. Select the main duct where perforation design is made and click on Copy Family or Copy All Families, and then select Other Ducts and then simply click Paste to replicate the design to other pieces. If you want to change any piece design, simply edit it using design parameters. Once done, simply verify the orifice placement in 3D Viewer to check their placements satisfy the project requirement. Once the air dispersion design is finalized, we can move to the next stage. In Chapter 3, we will verify the designed air dispersion system using CFD analysis and understand how the air is actually distributed inside the space.